Good morning, everyone. Yes, I do. I do like to ride my bike. This is one of my bikes. It is a Cannondale Slice. If you look closely, you can see it has what are known as, I mean, you're asking, so I presume you have some idea of cycling. This is a time trial or a triathlon bike. It's got these handlebars out front, so for aerodynamics. Um, and I do love to get onto it. Thank you very much. I like it. Okay, everyone. So I have our slide deck open. I'm going to share that in just a second. Um, then the next thing is, oh, no, not that. I need to switch my screen to no, screen three. There we go. Save. All right. Um, So the first thing that I wanted to make note of for y'all is that you have to have, or you have a discussion due tonight at 11:59 p.m. That is up. Please go ahead and do it. At this point, 76 folks have completed theirs out of, I think, 100. I think we might have a solid 150 in this class. So make sure you do that. In addition to that, you have quiz number two that is due tonight. And somebody asked me a little while ago, and I presume other people might have this question as well. How many times can you do it? The answer is you have two attempts. The higher grade, the higher of your two attempts will be the one that's recorded in the grade book, not the most recent one or not the lowest one. Um, there's that. Then one other thing that I wanted to mention is that there is at least one question where um, are we allowed to resubmit our discussions? I don't know that you can delete a discussion. I'll look into that. Um, delete. I think that you can delete your discussion entry and add them. Yeah, Marvin, thank you very much. You can add them. Okay, so for quiz number two, I'd like you to go, no conversion charts, no notes or anything like that. Um, but after you take your first attempt of the quiz, then you can think about it and say, oh, well, this is a question about converting from Kelvin to degrees Celsius. I should probably look back at that and make sure that I know that conversion. Or, oh, this asked me about kilometers to meters or meters to kilometers. Can I do that? Um, I'm still writing this note, but I suppose I don't need it. You can edit your discussions. Just make sure that when you delete one, make sure that you actually resubmit one. Um, the other item is I've gotten an email from a handful of people that, hey, I selected um, this answer because there's duplicate answers. I think one of them's right, and I got it marked wrong. And yes, that is something that I looked back at, and sure enough, there is at least one question where there are duplicate answers, but only one of them is marked correct. I want you to be absolutely clear that um, after the window for taking the quizzes is completely closed, I'm going to go ahead and go back and click to accept both of those right answers. So in the event that you're like, hey, I should have 4 extra points or 4 additional points on my quiz grade, um, I will, email me and I'll go ahead and make the change so that your score is up to date. But I will also make sure that if you're like, hey, he said that, on Saturday morning, I will go back and make that edit. And I mentioned Saturday because remember, the quizzes are due tonight, but if you miss that, you can still complete the quiz again, you can still complete the quiz, though there's a late penalty if you do it tomorrow or Friday. Um, are we allowed scratch paper on quizzes? Yes, you are. Would you say the questions are similar for each attempt or are they completely different? They're very similar to one another. And I wouldn't say that it's like changing numbers, but um, I've got them kind of grouped out. Like this is a kind of the skills that I want you to take away from this. So there is like a group of questions that are converting from Kelvin to Celsius. And then there's another group of questions that are converting from Celsius to Kelvin. Those are things that I want you to be comfortable doing. And so I didn't go crazy on like, oh, well, this is completely different. Okay. I saw you went back on mine, said it was marked right. Yes, I'm going to do that as people email me. And then I'm going to make sure that everyone gets the points that they're earned or that are deserved. The thing is, whenever I make the change, then every person who takes the quiz after that, theirs doesn't register immediately. Will today's class material be on the quiz? Or is it or is it up to what we covered on Monday? The quiz was posted Monday morning. And so this is the case moving forward. All of your quizzes are going to be up Monday morning at 8 a.m. And so what that means is they're only going to be over stuff that you have previously covered. So the timing of our class, the Monday morning section at 9:30, the content there will not be on that week's quiz. I hope that makes sense. Could everyone give me a 5 in the chat if they understand that, and any other character that they don't understand? Okay. Are we still on chapter two? Are we moving on to chapter three? That's a great question. I'm going to tackle a little bit of stuff on chapter number two before we move on to chapter three. Um, I just wanted to go back over those last few slides. The upcoming Monday? So the quiz that I post on Monday will cover stuff from today and Monday and our most recent two classes. Does that make sense? Okay. If something is a little bit confusing about that, just let me know. I understand that, you guys have multiple classes and um, it's always kind of tough. Like, well, this professor said this professor said this professor said we could take the quiz unlimited times. This guy said two times. Oh, rats, who said what? So if anything comes up, please don't hesitate to let me know. So I'm on slide 16 of the chapter two slide deck. And in this, what we're doing is we're looking at atoms compared to molecules. I have good news for everyone, and maybe you guys didn't have this issue in class last week, but I figured out some of the issues with my tablet, so it won't be writing all crazy. Okay, so a molecule is a group of atoms chemically bonded to one another. So what that means is that these two atoms, this one and this one, have something that they share to bring them close together. Now, this is a what's known as a space fill model of a molecule. How about model? MODEL, Joel. Then chat. Sorry, just have to make sure that I got all my stuff. I apologize. Okay. Okay. Um, I'm a little confused. The extra points for the quiz, how do we get them? Um, I've given the Proctorio practice quiz as extra credit opportunities, and those are for your final exam. If you completed those, you'll get credit for those, but those won't be added until the final exam. Okay, so this is known as a space fill model. Another way that you could look at this is look at the individual atoms, and then you use like a symbolic representation where you say, okay, well, on the periodic table, oxygen is represented by O, and then we've got hydrogen represented by H. And we draw this little arrow, or not arrow, but we draw these lines connecting these two things. And so this line represents sharing of something between the oxygen and hydrogen atoms. And this right here is commonly known as a bond. And we refer to this as a bond. So this, I would say something like, well, this has one, two oxygen hydrogen bonds. Now over here, we've got carbon and oxygen and oxygen. And this is getting a little bit ahead, but this is just kind of planting a seed. This is what's known as a double bond. This is also a double bond. Now, there are circumstances where a double bond is not necessarily preferred, but more accurate than a single bond. In which case, you could say that this is a carbon oxygen double bond, and this is a carbon oxygen double bond. Now, these are two simple molecules, water and carbon dioxide. I'm going to drink some water as a part of my coffee, and then I'm going to exhale some carbon dioxide as my body breaks down fats and breaks down sugars, goes through what's known as cellular metabolism. Now, these molecules can get much more complicated, as is seen here. We've got caffeine. Caffeine has nitrogen. Here is one example of a nitrogen. Oxygen, these red balls, spheres, whatever you want to call them. Carbon, represented by the black balls, and then hydrogen, represented by the white ones. Now, these are not colors that you have to memorize or anything like that, but um, these are not colors that you have to memorize and associate or anything like that. But this is a pretty common, and there are standard colors for visualizing and representing these. I got a private message question. My profile is flagged on my PC. Is my SSO correct on the mobile? I don't really know how, I don't know the answer to that question. I'm sorry. Um, but you're on Zoom at the moment, so that's what I can tell you. I would contact ITAC at txstate.edu because you're that's beyond my technical understanding. Okay, so if we wanted to draw or write out this molecule, convert this from this structural formula, we could say, well, this is one molecule of, and then we count up all the individual atoms. Now, this molecule has a common name of caffeine, and this has a chemical formula where we write out basically each of the individual atoms. C, N, H, and O. You can log into Zoom with your net ID, then okay. Great. Um, Thank you for sharing that, Grayson. We have one, two, three, four, five, six, seven, eight. Eight carbons. Next up, I've got nitrogen written, and we have a total of one, two, three, four nitrogens, so N4. Then my hydrogens, I've got one, two, three here. Then I've got one, two, three here. There we go. And then one, two, three, and one. Okay, so that gives me three groups of three and one. So that puts me at 10 hydrogens. Vivian, that's a fantastic question. How do we know what order to list the atoms when we write them in the format I'm currently doing? There are some conventions and there are some rules. One rule that I think you should just kind of treat as this is the rule I'm going to follow is atoms farthest, Farthest, left go first. There is, however, an exception. Any rule comes with exceptions. Speed limit's a rule. West Texas, you have an exception though, because who wants to drive in West Texas at like 55 miles an hour? I know the speed limit's not 55, it's like 75 out there. Our exception to this rule is hydrogen. So we're going to write hydrogen. Hydrogen is typically not going to be the first. Now, I kind of did these in a little bit of a haphazard and random way. In fact, I was so haphazard, I forgot to write the number of oxygens. Typically, what you're going to do is carbon, then hydrogen, and then everything else moving from left to right on the periodic table. And if you look at the periodic table, which you may or may not have before you, but remember one resource that I think is really good to go to for a good picture is ptable.com. If you look at that, you'll see that N is farther left on the periodic table than oxygen. So nitrogen, then oxygen when you're moving from left to right. So I hope that answers and clarifies your question or clarifies anything with regards to that. So I'm typically going to write hydrogen second. And in large part, that's because, well, you're more times than not, that hydrogen is going to be bound to the kind of most abundant atom, whether that's carbon or nitrogen. And in this case, carbon is pretty much the most abundant. If you look at all those hydrogens, like here, and then here, and here, I did circle those, but um, you'll see that carbon is bound to hydrogen. Okay, now what I want to do, there we go, it pops up now, is I want to look at this expression. When you have multiple of something, um, what we have here is, well, we've got oxygen, hydrogen, hydrogen, and we've got three of them. And we want to write H2O because that's the molecule or the substance that we're talking about and that we're interested in. But what you do not do is take the number of these independent and individual molecules and apply that to each one of them. And what I mean by that is we want to indicate and signify that there are three H2O molecules, but the way we do it is by writing a number out front. This is known as a coefficient. So that three applies to kind of your calculation of how many of these different atoms are present. Now, it, you use that information to say something like, well, there are three water molecules. But if I were to ask the question, hey, you've got three water molecules, how many hydrogens are in each water molecule? I'm individualizing or signifying a specific one of them. So for that question, you would say, okay, well, in each water molecule, there are two hydrogens and one oxygen. I just want to distinguish that from, oh, okay, well, I know how to do this. I'm going to write this as H6O3. This right here, H6O3 would be a completely different molecule than three H2Os. Because when you group all of these atoms together, you're kind of suggesting that they're bound to one another. So if you were to say, oh, I've got a molecule of H6O3, then essentially what you're doing is you're saying, okay, well, I've got this molecule right here. There's boom, 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 boom. Essentially, that's what you're talking about. So could everyone give me a Y in the chat if you understand the difference between the 3H2O and H6O3, and an M in the chat if, wait a minute. So the three we use as a coefficient to indicate there are this many of this molecule. This is our molecule. And if you were to say that, then you could say, well, how many of each atom are there? And you could apply that and say, well, the total hydrogen count is this. The total oxygen count is this. So this three right here applies to, well, how many of this thing are there? I think that it's helpful to say, and I'm going to draw something that I hope kind of makes sense. Erase all the ink on the slide. Oh. I try to think about molecules as individual units. So I'm going to draw, because it was mentioned earlier, I'm going to draw a bicycle. There's one, two. These bicycles are getting lower and lower quality as I go through here. Sorry about that. Okay, so would everyone agree with me? Give me a one in the chat if you agree that this is a bike. Okay. Now, you could look at each bike and say bike equals, and I'm trying to do my best caveman talk, caveman speech. Two wheel. plus 1 frame. Okay. Now, if I were to say 3 bike, you would know that, or I like to think that you'd say, okay, well, that expression is this right here, as opposed to something like this. Granted, I'm drawing what I think would be a very fun, exciting, and dangerous and cool bike. And that got me. I've got 4 wheels, so I'm gonna add one here and I'm gonna add one here. So the 3 is applying to how many of the individual units are there? How many of the individual things are there? And then if you're trying to take an inventory of what are the building blocks for those, then you can use that 3 to multiply up. But you're not going to say, well, this is H6O3. I hope that made sense as opposed to making it more confusing. Okay, so as an example, we threw this one up last time as a poll question. And I'm going to get you the poll questions for day after we finish this slide deck. How many hydrogens are in ibuprofen? Well, there's 13. If this molecule is ibuprofen, there's 13 carbons, and there are D 18 hydrogens. Okay. That number, these numbers are known as subscripts. They are lower than the font line, so this is a subscript, or these are subscripts. Now, here what we have is, well, a good question that is taking an inventory of everything. And this could be asked a couple of different ways, or there are a couple of different questions that I could use for this. One question is, well, how many ibuprofen molecules are we talking about? 3. If this is a molecule of ibuprofen, you'd say, oh, well, there's 3 ibuprofen molecules. But this question is asking about, well, how many total of a given atom are there? And the atom that we're interested in is hydrogen. So how many hydrogens are there? Well, in that case, you take the 3 and you multiply it by the subscripts. And you say, oh, well, 3 times 18 is 54. Okay. Now, I'm going to go ahead and open up the next slide deck. So we are moving on to chapter number 3. But before I do that, I want to give you guys, I'm going to close this out. I'm going to discard my ink. And now I'm going to screen sharing stop. Thank you very much, Zoom. I'm going to open up the starter questions for today. Starters launch. There's 3 questions that should be popping up. And these are ones where I'm just trying to see what information you have about these different topics or these different items. Now I'm going to go to share my screen. Okay. Well, these questions have been up for a minute. I'm going to leave them up for about 5 minutes, roughly, just so that folks can finish them. But now I'm going to go ahead and jump in. I'm going to let you guys know that at this point in time, the most popular answers or the correct answer. Okay, I don't see the questions. As somebody has sent me a private message. There is something that is a circle with 3 dots. If you're on the mobile device, you might have to tap your screen and then you can see your menu. That menu includes either just the word more or a circle with 3 dots in it. tap that, and then underneath that, you should find polls. If it's not coming up there, you should look for anything that says polls. I'm going to leave this up for 5 minutes. So you got about 3 more minutes to get your response for those in. Um, so, and this is just a good troubleshooting opportunity. So, atomic structure is what we're getting into. The correct answers at this point in time are the most popular answers, which is pretty awesome. Now, with that in mind, um, the idea of the atom has been around for quite some time, and it has evolved quite a bit. Um, in particular, there was initially this idea of, oh, well, an atom is just this this sphere. Everything's made up of atoms. Cool. What properties do we know about it? I don't know. It's got them though, I think. At some point, people kind of concluded that, oh, well, you know what? There are positive and negative features or charges or properties of an atom. So that's where we get this model right here. So this is our evolution of our model over time. And this model was known as the plum pudding model. Now, I have never had plum pudding. I don't really like plums. So it's not something I've ever sought out. But I think that it's also a kind of a British or an English, I don't know if I would say delicacy. I'm not going to say delicacy. Like an English dessert, which based on what I've seen on the internet of the big British breakfast, not interested. I don't think I need beans and whatever, toast. Anyway, so this is the plum pudding model. And the idea here is that, well, the overall thing has a positive charge, but then there's randomly kind of peppered throughout negative charges. And so we've got positive features and negative features, and well, the negative features are just kind of randomly dispersed. Now, I'm going to go to this so that I can access this link and share it with you guys. Um, so at some point, there was this guy named Ernest Rutherford, and he said, okay, we've got this plum pudding model of a atom. I like it. But as is when we have any sort of theory or any sort of model, I think we should investigate the kind of validity of this model. And so we've got this depiction right here in the center of the screen. I'm sharing, yep, sharing the web browser. We've got this thing right here, which is our model of an atom. And what Ernest Rutherford said was, you know what? I'm going to get a piece of gold foil. And what I'm going to do is I'm going to get alpha particles. These alpha particles, I'm going to fire at this gold foil. I'm going to fire these alpha particles. And you know what? If we've got negative charges randomly distributed, just kind of randomly peppered out, then if I have a method of detection over here to detect these alpha particles, well, then these alpha particles will basically land in the opposite space from where they were fired. Okay. Now, I don't want you to get lost in the terminology here, but I want you to think about this as Ernest Rutherford was saying, I'm going to shoot a BB from this point right here. And if and these BBs will ricochet or deflect off of negative charges if they're randomly distributed, or they'll kind of avoid them, and those BBs will end up directly opposite from where I'm firing them. Could everyone give me a emoji if they understand that the alpha particles are just BBs, and if the plum pudding model is correct, they will land directly opposite of where they were fired from? Okay. Now, this is the idea with a plum pudding model. And Rutherford he didn't really have a horse in the race or anything like that, where he's like, well, I didn't make up the plum pudding model, so this has to be wrong. But he did say, listen, if the plum pudding model is not right, and instead these electrons or these negatively charged things kind of have an order or an organization to them, well, then we're going to be able to detect them at different locations from where they were fired. So here's this model for the Rutherford atom. Again, he's firing alpha particles, which are the BBs, toward these atoms of gold. And then he has methods of detecting those alpha particles kind of all around him. So the idea was that, listen, I'm going to fire this BB, fire these BBs, and if they hit something that they're going to ricochet off of, I should detect them here, 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 and here. If the plum pudding model is right, they're going to be up here. So you could, for the purposes of the Super Bowl week, well, I'm going to fire them from one end zone. They're going to end up in the other end zone if the plum pudding model is right. If the plum pudding model is not right, I'm going to throw them from one end zone. They're going to end up randomly throughout the stadium. I feel like that was a little bit more sensible. Okay. So what ultimately happened is that Rutherford's experiments disproved the plum pudding model. More significantly, what they did was they validated or kind of confirmed this other model, a more kind of classical model for a atom. Okay, I'm going to end the poll. I'm not going to share it. Well, I'll share the results. I'll share the results in just a moment. But Rutherford ultimately concluded that, hey, we've got electrons that are kind of encircling the nucleus, and the nucleus is where we have our positive features, and that is much like a cell's nucleus, kind of centered in the center of these individual atoms. So this whole thing is an atom, and the positive region is in the direct middle of it. So Rutherford was like, sorry guys, frowny face on the plum pudding model. Now we have this atomic structure where there's a nucleus that has your positive features, and that's in the center of it. Now, that's great and that's wonderful. I'm going to take a pause now to share the results of the starter questions. The first starter question was, which part of the atom accounts for most of its mass? The correct answer is the nucleus. Two atoms, question number two atoms are the same element if they have the same number of, the correct answer is protons. And number three is, which subatomic particle is primarily responsible for chemical behavior? And the correct answer for that is electrons. So the mass is in the nucleus, which we'll see a little bit more in just a moment. Two atoms of the same element have the same number of protons, and the electrons give your chemical behavior of an atom. Okay, I stop my share right now, and instead we're going to jump now to this, identifying those subatomic particles. Your subatomic particles are the protons, neutrons, and electrons. What's important to know about these different things is, first of all, protons and neutrons have mass. Those are the ones that kind of determine what the mass of an atom is. An electron basically has no mass whatsoever. Okay. Protons and neutrons, well, protons are positively charged, electrons are negatively charged. So the way that I always kind of think about this and try to remember this is that for mass, you've got protons and neutrons. Electrons have no mass. For charge, protons and electrons, those have charges. Neutrons have no charge. I also like neutrons because, well, another substitute word I say for that is neutral. Neutrons are neutral. They have no charge whatsoever. Now, the location of these things. Just like we had as that starter question, which part of the atom accounts for most of its mass? The nucleus. That's the kind of part of an atom that has the mass. Electrons, they basically have no mass whatsoever. The nucleus is where your protons and neutrons are. Outside of the nucleus is where your electrons are, and well, they don't really have any mass, so they don't contribute to that. Now, some important things to know. Your number of protons is the same as the atomic number which gives the identity of an element. Your number of neutrons is equal to your mass number minus your protons. And we're going to look at the periodic table. I mentioned this last time, but we're going to look at the periodic table and look at some of these numbers as well. Your number of electrons is equal to the number of protons for neutral atoms. So what that means is that if I said, hey, you've got carbon, I'm going to say neutral carbon. And I said carbon has an atomic number of 6. That's 6. And I want you to know about the magnitude of this. That's 6 positive charges. Okay. So if you have a neutral carbon, that means you have 6 protons and 6 electrons. Because these negatively charged electrons cancel out, charge-wise, the positively charged protons. Now, if I said you have neutral carbon, and I said you have 6 protons, 6 electrons, does that give you any information about the number of neutrons? Give me a Y or N. Just that statement. It doesn't. It does not. If I said, hey, you have neutral magnesium, and I didn't give you a periodic table, I said magnesium has, let's say that it's got 9 protons. I've actually given you no information about the number of neutrons it has. If I said that it was a neutral atom, I've told you about the number of protons and electrons and said that basically those are equal, but I haven't told you anything about the mass. Now, the first term that I want you to be familiar with is this one, the first big term with respect to atoms is this one right here, isotope or isotopes. If you are a baseball fan, you might be familiar with the Albuquerque isotopes. If you're an Albuquerque fan, you might also be familiar with the Albuquerque isotopes. Or if you're a Simpsons fan, you might be familiar with the Springfield isotopes, which are a minor league baseball team. Now, in addition to being a minor league baseball team, isotopes are examples of atoms with the same number of protons but different number of neutrons. Now, I want to go ahead and scribble this out. So ignore the stuff that I've scribbled out. You don't see it. This one right here. Could anyone tell me what is the mass of this atom that I've put a star by? I'm seeing ones. Great. Okay. Now that is an example of an isotope of hydrogen. That is the isotope known as the 1 isotope of hydrogen. Okay. Now, next up, what is the mass of this atom of hydrogen? 3. Proton, neutron, neutron. Done. Spoiler, or I hate to be a disappointment, but that's also hydrogen. Wait a minute. These are both hydrogen? Huh? And then if we go to this one in the middle, the mass of that is 2, and this is also hydrogen. So these are all examples of hydrogen atoms. But there's one subatomic particle that is the most important for that identity, and that is our protons. The number of protons never changed here. Each one of these atoms has 1 proton. Now, the number of neutrons did change, but that did not change the identity of the atom. So essentially what that means is if I gave you a hypothetical atom and I said, hey, here is, I'm going to draw just the nucleus, P, 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 N, N. Can you tell me what is the mass of that nucleus right there? 5. Okay. What about this one? P, N, 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 N. What's the mass of this nucleus? Right here. It's also 5. Are these two atoms, give me a Y or N, are these two atoms the same atom? Or do they have the same identity? No, they don't. I'm seeing pretty much no's across the board. Great job. The reason they are not is because if we look at atom A versus atom B, atom A has 3 protons, atom B has 1 proton. So they are different because of the number of protons. Now, if we look down at hydrogen here, hydrogen 1, hydrogen 2, hydrogen 3, these have unique names. You don't have to know these. These are isotopic names. This is hydrogen. Hydrogen 2 is also known as deuterium, and hydrogen 3 is also known as tritium. Now, those are just special names to indicate the differences between these. What I want you guys to be able to do is to see a question like this. And here's our first mid question for the day. How many protons are in carbon 14? And you would have the periodic table on an exam, but I'm going to give you this one. Let's see. Carbon has an atomic number of 6. So if we looked at the symbol for carbon, it would look like this, 6 and 14. Let's try to erase that. Strong showing by the correct answer, which is awesome. Okay, so it's about 50 seconds. I'm going to go ahead and explain this one, and we're going to get to the bottom of it. Okay, so when we look at all these numbers, we've got, well, the only number that's shown on this slide is 14. And it might be tempting to be like, ooh, 14, that's what I'm looking for. But that is the mass. So that's like saying you have a carbon atom that has a mass of 14. Now, the units for that would be AMU. What we need to do is kind of ignore that and instead say, okay, carbon, that's what I'm interested in. I can find that on the periodic table and see, oh, there's the C. And okay, well, 14, that is my mass. And I can determine the number of protons. Well, heck, I don't even care about that. What I care about is the atomic number, the whole number that is on the periodic table. Okay. Now, so the correct answer is A6. The second most popular answer was C. I will give everyone who is in the Zoom 1 bonus point if in the chat someone can answer what or how many. There are 8 of something. What is the subatomic particle? Oh, done. There are 8 neutrons. Great job. I'm going to make a note. 1 bonus point. This is 2/4/2026. Okay, great. So you're absolutely correct. There are 8 neutrons. That's where that 14 comes from. Now, if you build an atom, essentially what you're doing is you're playing around with these different things. You're taking protons, neutrons, throwing them in, and then the electrons are going to be in the outer area. Those are your negatively charged things. Now, an atomic symbol is going to have a couple of different things. It's going to have your mass number. It's going to have, that is your number of protons plus neutrons. It's going to have your atomic number. This is the number of protons. Then your charge. Charge is maybe something you won't see very often. This is something that I want you to be able to deduce. So I want you to be able to deduce from the question, what is the charge and what is the number of neutrons in a given atom or in a given isotope. Now, one of the things that is always tricky is if we see something like carbon 12.0111, Or if you pull up another periodic table, you might see 12.0. You might see 12.01. You might see 12.000000009. A fair question is why? And the reason for that is because that is the weighted average of the isotopic masses or the isotopic masses. Now, this is a calculation that isn't too tricky, but I want you guys to be able to do. And this is a part of the discussion today, or that will be posted at noon. So, the way that you do this calculation is you take into account a couple of different things. The first thing is the number of different isotopes. And this would be, you would see this in the question. Second would be, what are the masses of the different isotopes? And then the last thing is, what is the percent abundance of the different isotopes? Different isotopes. So I think that you guys all, um, I'll give you an example. Let's say that in your house, and this is really the example that I'm giving is I want you guys to think about the word abundance. Um, I have, okay, in my household right now, I have two dogs, one fish, one bearded dragon, bearded dragon lizard, and six people. The six people being me and my wife and our four boys. Which of these things, which of these living things is most abundant in our household? Add it to the chat. People. Perfect. So now I'm going to switch this a little bit. And I'm going to use percentages. I'm going to say that we have a sulfur atom with a mass of 30, another sulfur atom with a mass of 32, and another sulfur atom with a mass of 41. I haven't written anything about the abundances, but now I'm going to write those percentages or the percent abundances. And I'm just coming up with kind of random numbers. Let's go with 15. Then let's go with 27, 27 plus 15, and 58%. Okay. Which one of these sulfur atoms is most abundant? And you can just write the number for the weight. Absolutely right. 41. Now, if I said, well, what is the average mass of a sulfur atom? I think that there's a temptation to just say, oh, okay, well, 30 plus 32 plus 41, divide by 3. Would that be correct? Y or N in the chat if I asked for the average mass? No, it would not. Okay. You know that. I'm seeing the responses and I'm seeing some of y'all in your video do this number. And I like that. That's like a don't do it. You know that's not right. Don't joke with us. And I'm not going to. If you were just taking those three numbers and dividing by 3, that would suggest they're an equal abundant or an equal abundance. That's not the case. This number with this long decimal place is your weighted average. So that takes into account the different abundances. Now, to do this calculation, let's go through our little checklist here. We did this in sort of a not sequential manner because I gave you the different isotopes. and their masses, and then through the abundances out there. How many different isotopes are there of sulfur from what I've shown you? Three. Okay. What are the masses of those isotopes? Well, there's 30, 32, and 41. Okay. What is the percent abundance of these different isotopes? Well, it's 15, 27, and 58. That all adds up to 100, I think. Yes, it does. It does. In order to figure out the weighted average, here's what we do. We take these percentages and we convert them to decimals. What I'm going to do is I'm going to write it in, let's see, I'm going to say down in the lower left-hand corner so I can avoid writing on top of stuff. Oh, no, I'll do it at the top. I'm going to do it at the top of the screen and hopefully it won't be too messy. I'm going to convert that 15 to 0.15. I'm going to put that in a parentheses. And then next to that, I'm going to put the mass of that specific isotope. What's the mass of that of the isotope that is 15% of the overall share? 30. Great. So I'm going to then put these in parentheses. And then I'm going to say plus. The next number that I'm going to do is use another decimal number. The next decimal number is the 0.27. The 27% converted to a decimal would be 0.27. I'm going to put that in parentheses. And actually, you know what? I'll make it a little bit cleaner. I'm going to not put these in individuals. Instead, I'm going to say times. So 0.15 times 30. And now I'm going to do 0.27 times, what should I do that by? Or multiply that by? 32. Great. And then I'm going to do, last but not least, 0.58 times 41. So could you give me a 9 in the chat if you follow the structure that I have right now? Wonderful. So we're going to do each one of these individually. So 0.15 times 30. It's going to give me 4.5. So I'll write that down below. 4.5. Then I'm going to do 0.27 times 32. That gives me 8.64. Last but not least is the 0.51 times 41. And that is 20.91. So I have those three numbers, and I'm going to add them up. 20.91 plus 8.64 plus 4.5 equals 34.05. That is the weighted average of sulfur atoms if these are the isotopes that we're interested in. Now, if you're looking at this and you're like, I understood the structure, but I don't understand how the 34.05, what does that mean? That relates to the abundances. We're weighing how common the different isotopes are. I always what's helpful for me is to change terms and say something like, well, I'm going to get rid of these, and instead I'm going to get Oreos. Come up with something where I say, okay, well, I'm going to ask people to give me Oreos, and 15% of the Oreos they give me are regular Oreos. 27% are double stuff Oreos. And then 58% are golden Oreos. All these have different masses. Let's say that the Oreos are 30, double stuffs are 32, and golden are 41 grams. Sorry, let me check my math again. 20.91 plus 8.64 plus 4.5. I got 34.05. I would take another look at I punched it in all correctly. So um so this is a sort of problem that you have as a discussion point today, or as your discussion, the one that is due on Friday. But heck, if you're going to do the discussion that's due tonight, do this one as well. Just knock them both out at once. Faith, I'm not sure. Some really 0.58 times 4. Did I do that one out? 0.58 times 4, 23.7. Faith is right because okay, thank you very much. Sorry about that. I apologize, everyone. My math was incorrect. It's not 20. Okay, so then 23.78. So then 23.78 plus 8.64 plus 4.5 is 36.92. Okay, thank you very much. Sorry about that, everyone. Okay, so this is a calculation that I want you to have as a skill to do. So make sure that you're capable of that. Next up is another Zoom poll. And actually, before I do that, I'd just like a quick survey. On a scale of 1 to 3, oh, I've got this now. 3 being, I'll need some practice. I'll probably feel better after the discussion. Okay. Okay, great. I'm saw some ones, I see some twos. Um, I would just treat this as, hey, I know I'm going to see this sort of problem. So this is like an absoluter. I'm in the middle, just need practice. Understandable. Um, okay. So next up is our poll question, our second mid poll question. Yes, activities will begin starting next week. So this question is, well, how many neutrons are in carbon 14? We know how many protons there are. Do you think you could do a quick reminder about the other two parts of the isotope question? I got a private message that says, do you think you could do a quick reminder about the other two parts of the isotope question? The other two parts being the numbers of isotopes. So I'm going to jump back while this question is up. Somebody sent a private message. Do you think you could do a quick reminder about the other two parts of the isotope question? I presume that means these two. So the number of different isotopes and the masses of isotopes. That would be information that would be provided in the problem. So that would be something like, the question would read, of the 4 isotopes of boron, they have masses of dot dot dot. And from that, I mean, there's a couple of ways that you could think about that. You could say, okay, well, I know that a boron atom always has 5 protons, but hey, there's one boron isotope that has a mass of 9. And give yourself the little kind of mental math question of, well, how many neutrons does that have? Well, this is going to have 5 protons and 4 neutrons. Okay. What about B10? Well, that's going to have 5 protons and 5 neutrons. That is not information. That's not critical information for answering the abundance and coming up with the mass average. but it is, I think, still worthwhile to be thinking about and giving yourself those little mental joggers of sorts. So B12, B10, B11, B12. So your question would read something like this. I'm going to put a quotation around that and erase this. It would be, here are the different isotopes. Does that help? Is that what you were looking for? Okay, great. So this poll question, how many neutrons are in carbon 14? I'm going to end the poll, share the results. The most popular answer was the correct answer, and that is 8. I stop my share because now we've got another question, and this question is mid-question number 3. How many electrons are in a neutral atom of carbon 14? Ooh. Well, we know carbon 14 has, and 3 people are throwing 14 as the answer. 4 people, 5, 7, 8. I keep raising the number because 14 is not right. 14 is not a good answer. The reason 14 is not a good answer is because 14 is the weight. So this number right here, this 14, is telling us the number of protons and neutrons. So pro plus neutrons. So we already did the question where we said, oh, well, this has 6 protons, 6 positives, and the number of neutrons is going to be that right there. So I got a private message that says, when you say carbon 14, I'm so confused. Where are we getting 14 from? That would be provided in the question, just as it's provided right here. And if you're thinking, well, what am I supposed to do with that? What you're supposed to do is recognize that whenever you see something like this, and so carbon versus carbon 14. When you see carbon versus carbon 14 versus carbon 13, I want you to see that and think, okay, well, what I'm referencing there and what is important there is this number. This number should stand out to me. And I'm going to go back just a second to look at this example right here. Here we have hydrogen 1, hydrogen 2, hydrogen 3. All of these numbers indicate the weight. So when you see, or when I say carbon 14, I'm referencing the weight. And what does the weight consist of? Well, the weight consists of the number of protons plus the number of neutrons. Does that help at all for the person who sent me that private message? Okay. So what's probably helpful is to, and I can pull this up. I'm going to switch my share. I'm going to show you the periodic table. And I will do some annotation on this. So when you see the periodic table, add to the chat, what are the numbers that you see um, in the square designated square for carbon? Add those numbers to the chat. 6 and 12. Perfect. Now, 6, this is our number of protons. Okay. The 12 is, you can, or that 12.011 That is the weighted mass average. And what that means is, for our purposes, so that is the number that says, hey, there's, you know, and I'm just giving you hypotheticals here. There are two, or no, let's say there are three carbon isotopes. Tell me in the chat, of all of these different isotopes, how many protons does each of these isotopes have? They all have six. Okay. Now, could anyone tell me what is the mass of at least one of those isotopes? I'll give you a little bit of a hint. It's not going to be 6, 12. Perfect. Well, not 12.0011, but we're just going to go with 12. Okay. So there's carbon 12. Could you tell me the mass of another isotope? We are not multiplying it by 2. That's a good question. I like that. So a different isotope of carbon, 14. Okay. C14. And then there's also, just to give you guys a little bit of additional information, there's also C13. So there's these three isotopes. I'm going to draw an atom of C12. And then I'm going to draw an atom of C13. And then I'm going to draw an atom of C14. But I'm just going to draw the nucleus. Okay? So, Vivian, you are spot on. You are absolutely right. And I'm going to go into that in just a second. So, I'm going to give myself a little box, and that is where I'm going to draw my nucleus for these different isotopes. For C12, I'm going to do a blue dot. Actually, I'll do a P. Proton, 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 proton. Okay. That's 6 protons. How many should I draw for the C13 isotope? 6. P, 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 P. Okay, then 14 is also going to P, 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 P. Okay. So I've got my 6 protons that are going to be in each one of these different isotopes' nucleus. Now, what else is found in a nucleus? I mean, you can give me a neutron. Perfect. So what I need to know is how many neutrons should I draw or should I write for my C12 isotope? 6. N, 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 and N. That's 6 of them. And then I probably need 7 for C13. 1, 2, 3, 4, 5, 6, 7. And then for 14, I need 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, if my abundance, so does this all make sense? Give me a 1 in the chat if you follow this, a 3 in the chat if that doesn't make any sense to me. Okay. Now, you can tell, or of these different isotopes, what is the average mass closest to? It's closest to 12. So this C12 isotope is going to be the most abundant compared to 13 and 14. If you were to think about this in terms of, or I always like to think about it in terms of exams, because you have exams and exams have different weights sometimes. Let's say that you had three tests in a class. E1, no, E1, E2, and E3. Let's say on exam one, which was worth 95% of your grade. Exam two was worth 4% of your grade, and exam three was worth 1% of your grade. On exam number one, let's say that you got a 100. And then exam two, you got a 5. And then exam three, you got a 1. Could everyone give me a rough estimation of what their grade is based on those numbers? You don't have to be precise. You don't have to do this calculation, but just kind of think about it quickly. I like it. Probably about a 98. It's probably going to be really high because it's going to be closest to the score that had the greatest weight. So similarly, when we look at the isotopic mass or the average mass, average weighted, or sorry, the weighted average mass on the periodic table, we can say, okay, well, there's these different isotopes. Um, what are we closest to? It's probably going to be closest to C12. I got a private message that says, will we be doing electron configurations in class, and will that be in this chapter? Yes, we will be doing. And it will be in this chapter. Okay, I hope that I was able to answer the questions related to this. Now what I'm going to do is go back to my slide deck, the question that we had. Minimize that. Okay, so we are going to just spend a minute looking at electrons in atoms. I've got to take a quick gander at my. Oh, that's wrong. No, wrong class. Cultures. Um, okay, so I'm gonna pop up the closer questions. Closer questions 2 and 3 are going to be stuff that over this last half of the class. So don't worry about, I mean, if you want to answer them, you can, but we haven't covered that content yet. I'm going to stop my share. I'm going to launch the closer questions. Again, question number 1 is the one that I'm most interested that you are able to answer at this point in time. Questions 2 and 3, I will share those with you and share the correct answers with you. But I don't expect you to be able to answer them at this point without, or sorry, based on what we've covered in lecture. So in the meantime, I'm going to launch those questions. Whenever you answer those questions, we're done. I hope you have a good afternoon. It's 10:43, so I just didn't want to try to rush in or rush through anything. Um, at any rate, I hope you have a great afternoon, and I will see you guys on Monday. Somebody sent me a private message. I just did the quiz. Is one of the answers literally wrong? I'm talking about. I actually talked about this at the beginning of class. So I've talked about the quiz questions. There is one that there's a duplicate answer, and I will fix that. Just shoot me an email and I will take care of it. And then I will make sure that everyone who has um, the correct answers or who, gets the credit that they're due. I apologize for that mistake. I will do my best to not let it happen again. Elements have I Mason, were you intending to copy and paste that somewhere else? Okay. Well, I'm going to stop the recording.